Hello, everybody. Welcome to my Game of Hierarchies show. As you can hear from my accent, I'm not from around. No, I'm not Canadian. I'm Austrian. That's why I put my lederhosen on. So I hope you appreciate what I'm doing here. Yeah, usual slides. If they drive, no, it's not working. What's the matter here? Please silence your phone. And this is serious because this lady is really laughing. I don't know. Looks like she's not taking this serious. Please silence your phones. And be reminded this PASS Summit is just one of many occasions or many events PASS is organizing. There's plenty of stuff out there. Most all of the things mentioned on this slide are free. So it's just finding out where to find the stuff, and then you can do your learning on your own for free. My name is Markus Ehrenmueller-Jensen, and as you can see, German-sounding name and Danish-sounding name, and my wife is from Denmark, so the second part of my name is from my wife. So I could do this session in English, in German, or in Danish. So feel free to ask in any question. We could also change to Danish to make this more like a 500 level session, if you want. Yeah, blah, 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 lots of tasks out there on the slide. But do you know what Tyrion Lannister would think about a speaker slide? He would think or say, every fool loves to hear that he's important. So much about the speaker slide. Who of you have seen the TV show Game of Thrones? Show hands. Okay, 2/3 of the room. Who did read the books? Usually there's less people, 1/3 of the room. And all the others just came to learn about GraphDB. Okay. Okay. For those who know the books and the TV show, if somebody in Old Valyrian asks you or greets you with Vala Morgulis, all men must die, what is the proper answer? Valado Heris, yes. All men must serve. And, you know, everyone knows there's Lannister always pays his debt, so you get a golden coin, chocolate. This keeps me moving. There's more chocolates to earn during the session, so please pay attention. So, let's see how often I can do this, jumping up there. If you didn't read the books or didn't see anything, there's no spoiler. Everything I'm showing here is like in the first book, in the first chapters. If you want to check out the books and the TV show, please check out the slides. For this 75 minutes, I brought 4 episodes. So one is like an introduction to GraphDB. What is graph? What are graphs? Why should we care about them? And then I will do a short intro what happened in 2017 when the feature was introduced into SQL Server, and then the 2019 new features. And as much as time we have, then afterwards we will see some advanced stuff where we can find out information about graphs. That's the idea. Who of you already had got his hand on SQL Graph 2017? Who already worked with 2017? A few hands, maybe 10, 15 people, not so many. So I was right in assuming I should do a short introduction what is GraphDB. So I have this in the thing there here. If you want to play around with the demos, please feel free to download, go to hierarchies.wordpress.com. You can download all the scripts where you can build up the demo things, and I think it's already uploaded to the PASS site where you can download the slides and the demo script, so you can also play around with the things I'm showing here. GraphDB 101. What are graphs? Graphs would be, for example, points of interest and routes in between. So in a graph, the point of interest would be a node or nodes, and the connection between those points of interest, the routes, would be edges. That's the terminology. The advantage compared to different other ways, you don't have to use GraphDB to model graphs in a relational database. The advantage compared to other ones is we have no redundancy, so every point of interest, every route is only there once. We have the possibility for unlimited amounts of levels, so we can just add new points of interest, we can add new routes, no problem at all. And we can model with the GraphDB not only graphs or hierarchies, but also many-to-many relationships, for example. Who heard about many-to-many relationships? Okay, yeah, everybody, okay, yeah. So usually would then split it up with the bridge table, and the bridge table is nothing else than the edge in our GraphDB. So maybe this helps you in understanding what the GraphDB is about. The disadvantage with the GraphDB, so there's no free lunch, there's still disadvantages. You still need joins. You have to join the nodes and the edges, so the points of interest with the routes in between. And to query, we have to use more or less complex queries. So we have to write loops, or we have to write recursive common table expressions. Or we could leverage the new feature from 2017 to write Cipher query language, CQL, which we'll see in a demo during the 75 minutes here. So what is a graph? A graph would be a node or another node, and the node is then connected with an edge. That would be a graph. To be honest, this is not really true, because a node is always a concrete example of something. So node, as a general term, would be not a node, but Eddard would, for example, be a node, and Rob would be another node, and Eddard is the father of Rob. That's what we see here as a graph. We can also model, for example, points of interest, so Winterfell, and we have Castle Servin, and there's a route in between. And we will see that there's an arrow, so there's the edge is going in one direction. This would be only true if this is a one-way. For many of the routes, for example, from Winterfell to Castle Servin, I cannot only go from Winterfell to Castle Servin, but also the way back again. And then we would not, this would be a directed, this is a directed graph, what we see here, but a graph which we can go over in both directions is not a bidirectional graph, but it's an undirected graph, and therefore we just remove the arrows. That's what the convention is. Point of interest are not hierarchies, so maybe we can add another point of interest and another point of interest, and then we have, for example, this situation that there's several ways of going through the graph. So we can go from Winterfell to Castle Servin and then to Moat Cailin, or we can go from Winterfell to White Harbor and then to Moat Cailin, or we can go from Winterfell to White Harbor, Castle Servin, and then Moat Cailin. Whatever, we can find the best route, and usually we speak about the shortest path. But what's short depends on your definition. So if you think about public transportation, maybe the amount of hops is what you want to minimize, because every time you change the means of transport, you have to wait in the rain, or you have the chance to miss the next connection. So we would optimize by the amount of hops. But you can also add weights, for example, miles or hours, or like costs if it's a toll road, and then you could optimize on those weights. So finding the shortest path in terms of miles, or shortest path in terms of time, or shortest path in terms of cost. This leads us to the features in 2017. So 2017, we can create nodes, and we create nodes by creating a table. Who of you has created a table already? I hope, okay. Who doesn't want to show his hands? Okay, you got tired, okay, I see. So create table, we create nodes by creating a table, and at the very end of the create table statement we already know, we put as node. That's how we create a node. Very, very easy. When we do that, then SQL Server automatically adds two additional columns, graph ID and $node ID, and I put graph ID in italic font, because we cannot work with this column. We cannot query it, we cannot change something there, we cannot remove it, it's just there. It's exposed in Management Studio, but we cannot touch it. But we can touch the node ID, the $node ID. When we create edges, what do you think? How do we create edges? Who was it first? This guy? Because you're closest, so you win a chocolate. So we can create edges by creating a table and put as edge at the very end. Welcome. So rather easy to create edges and nodes in the graph, therefore. For edges, we have lots of columns there, graph ID from blah, 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 in italic. So we don't care about these columns because we're not allowed to touch. And we have this $edge ID, $from ID, and $to ID. And that's the columns we'll work with. If you take a look, if I created this point of interest table and the route table. The point of interest table I created as a create table statement with the columns ID and name. And then the graph ID and the $node ID is automatically added. And as you can see, I did lie to you because the column is not called $node ID, but it's called $node ID 163 blah, blah, blah. Please don't use the postfix, always referred as $node ID, because as soon as you recreate the table, for example, when you move everything to production, then you create the tables there, there's a big chance that the table name is not node ID underscore 163, but a different thing. And this would then break your queries and your statements. So please never refer the full name, but always like $node ID. For the edge table, I created attributes there. They are not mandatory. So if you create a if you create a node table, you have to have at least one column for the edges. The columns, additional columns are optional. I created one with the road name and 3 weights, miles by land, miles by water, and miles by miles, total miles. And then we got all the other columns there. And again, $edge ID, $from ID, $to ID, you can refer to them, and you should refer with them without the long postfix afterwards. And here we can see how this is connected. So the $node ID is referred from the edge in the from ID and in the to ID. So 2 nodes are connected with the edge by referring to the node ID of the node. And as we can see here, there's from ID, to ID. So this is always a directed graph. We can only create directed graphs in SQL Server. Let's do a demo so we can see this. Actually, if we open up Management Studio and we have the new SQL 2019, and there's the Game of Thrones, Game of Hierarchies, and here we go for the graph thing. So in Management Studio, I think 17 something, we have this new folder here, graph tables. That's where the graph tables are hidden. We open up this, then we see 2 different icons. So one is like a big blue circle. That should be a node referred in our graph. And the other ones are like circles, and there's like a line in between. And this depends on your background. So some people see glasses, other people see handcuffs, but this is edges. This is an edge table. And we can see then, let's stick with the point of interest. Point of interest, we have those columns here, the graph ID, the node ID, and different other columns there. And if I create, for example, a select statement, then we'll see Management Studio is smart enough to not use the graph ID. It only shows the node ID here. And you should always change the statement to remove the last part here. So that's how we can query the node table. Is this working? Pressing F5. So here we go. I'm in Zoom it. That's what's confusing me. So I've got the tables here. So the content of the table.
Can we do this in Azure Data Studio as well?
Azure Data Studio, yes, you can query the tables. I have Azure Data Studio open in the other session. Let's try how this is invoked here. I'm rather new to the Azure Data Studio, so I will check afterwards how you can find this. Of course, you can write the queries there, but I'm not sure how this is like showed the graph table. But you get, of course, you get a chocolate for that question. I want to have this rather interactive. Even I could not answer your question, you earn a chocolate as well. So let's go back to the slides. So what is now the SQL Server GraphDB? The really nice thing with the GraphDB in SQL Server, that's what I think Microsoft is really, really, really good at, is to integrate new stuff into existing technology. So SQL Server, everybody knows SQL Server here in the room. So you have like a backup, you have column store indexes, you can have machine learning, row-level security, you name it. And the GraphDB is just tables in there. So if you already have your backup system running, the graph tables are automatically backed. You can, of course, increase the performance of your tables by adding indexes, column store indexes, and so forth. The graph is just a collection of nodes and edges, and as you have seen, the nodes and edges are just tables with a postfix S node, S edge, and that's how we create the stuff here. Technically, there's exactly one graph per database, so you could connect all of your graph and edge tables as you will, and you cannot do cross-database queries because a graph in one database is a different thing like a graph in the other database. Then we have this match extension, which we will see in a minute. And SQL or GraphDB was introduced in SQL Server 2017, and it was extended in 2019 with very nice features, as we will see. So what is this match clause? The match clause is a pattern matching. So I describe which pattern I'm looking for in my graph. I can also write multi-hop queries, so this is not only connecting one node with another node, but I could have connected several amounts of nodes if I want to and if I need to. And the language which is implemented in SQL Server 2017 and 2019 is Cipher query language, which was created by Neo Technology for their GraphDB graph database Neo4j. It is open source, so Microsoft could use this. And we have now this match extension in the select and where clause. Unfortunately, there's also another type of graph queries available. This is Gremlin. If you're using Cosmos DB, it's not SQL, it's not Cipher query language, but it's Gremlin. It's a different language, different syntax, totally different thing. This is not supported in SQL Server, in the other way around. So how do you write Cipher query language? If you look at this simple graph, we have two nodes and one edge in between. Father is father of child. If we would write this down without any graphic tools, but with ASCII, with the keyboard only, probably would look like that. So we have the node father on the one end, the node child on the other end. In between, in parentheses, is the name of the edge, is father of. And then we have like this minus symbol. This is not a minus, this is the beginning of the arrow here. And this is not minus greater, but this is the end of the arrow. So like the arrow is pointing from father to child. And that's exactly how you write your match clauses. Those match clauses can go in both directions, so we can have like the node is pointing to the other node in this direction, or we can have the node is pointed to from the other node, or we can even write queries where I'm looking for edges which is connecting both of them, so the direction is going in both directions. Some restrictions are applied, and there are workarounds available, so you will easily find them, or I can show you after the session. Currently, I didn't have planned time for showing you the workaround for OR and NOT, which is not supported. And derived tables are not supported in SQL 2017, so we cannot write common table expressions, or we cannot use a subquery, and using this subquery as referring the subquery as a node or as an edge. This is not possible in 2017, but it's possible in 2019. So Cipher query language. How does this work? So I've got this simple table. We already have seen it, the point of interest table, and I have the ID and point of interest name. So I typed in 148 rows when I did bore myself sometime in the past. And we have this $node ID, and we have already seen this. And the $node ID is a character, a string. And we can even read this. This is JSON. JSON is so much better than XML, isn't it? So what we can see here, this is type is node. Of course, we're querying the node table. The schema is DBO, because the table resides in the schema DBO. And the name of the table is point of interest, POI. And then I get this ID, which starts at 0. And this is only by accident, because I inserted the rows like in exactly this order. But those IDs are not connected. So the ID is not always my own ID minus 1. This is only by accident. For the edges, it looks similar. So I have the edge ID here in the front. The type is edge. The schema is DBO. The table is route, because my edge table is called route. And this edge table is connecting from ID and to ID. So from ID is referring a node. As you can see here, type is node. And this is ID 33, for example. And node 33 is connected with node, can we see this here, 36. That's how they are connected. And then we can see that can everybody see this? This always duplicates. 240 miles, 240 miles, 40 miles, 40 miles. Can everybody see this? This is because I connected the node 33 with the node 36, from 33 to node 36. And I also inserted one row for connected 36 with 33. So that's how that's my workaround, not having undirected graphs. I only have directed graphs. And because we only have directed graphs, we can either always query like, can I find something in this direction, or union, do the same, looking in the other direction. That's one way. But I wanted to have the queries, like the queries should be more readable, because I do not want to present long queries here in this demo. So I decided to just increase the row size, the amount of rows. So I have like, if I connected to 2 points of interest, I connected in both ways. So A to B and B to A, so it's much easier to query it in afterwards. That's why you see these duplicates here. And As we know, the route and the edge and the node are just normal tables. Of course, we can write joins. So I can write, even this is a GraphDB, I can write a query which is from point of interest joining the route with using the from ID and node ID. And you see, I did not use the postfix there, and joining then the route with the to ID of the route to the next point of interest. So we get like a list of ways I can directly go. I can directly go from Castle and Rock to Golden Tooth, 214 miles. And I also inserted it the other way around, Golden Tooth to Castle Rock, 240 miles. To get rid of these duplicates, I changed something here. I introduced this little guy here. I don't care which one I want to see. I just want to see one of those both ways. So I limit the list to the point of interest name has to be lower than the other one. So A, the name of A should be lower than the name of B. And that's how I get a list of directly connected nodes and without the duplicates. And then it's getting a little bit weird. So I'm not sure. Have you ever seen, who has seen a from which is listing names of tables? Okay. Wow, lots of old guys here. Yeah. Now I feel young again. Yeah. Sorry, yeah, should not offend you. I also learned this. So like in school, I learned like not the joins, but writing SQL queries. Then I went to university and worked without any SQL. And then I returned to SQL and was wondering, what is this join thing about? And then I found, this is like ANSI 92. This is after I learned SQL. And now I'm reminded what I learned in school many, many years ago. So this is a valid, for everybody who's not familiar with that, this is a valid statement. I can join tables by just listing them in the from clause. And everything which you would have used in the on statement of the join, I just put down on the where clause. So I'm still joining route from ID with A node ID and B node ID with route to ID. And then you have this where clause where we get rid of the twins. Why I'm showing this to you? The reason is because when we're writing the match clause, we have to write pre-ANSI joins without any joins. If you want to use GraphDB with the match clause, you have to learn or relearn the stuff joining tables in the from clause. And now we have this match clause here. And the match clause is exactly what we have seen on the slide. So I'm looking for a pattern where A is connected over route to B. And that's what we're getting. So if we execute this one, we get the same list as previously, but now we're leveraging the match clause. Has anybody worked with hierarchy, played around with hierarchy? Okay, a few hands, 10 hands. Who has hierarchy in production? Okay, still a few hands. Okay, okay. Usually it's not very adapted out in the market. For everybody who has worked or works with hierarchy, this slide is for you, so you can see the comparison between hierarchy and GraphDB. All the others, I would recommend check out first SQL GraphDB, and if this is not fulfilling your needs, then maybe you check out the hierarchy. But I would rather go first for GraphDB. So in 2017, we have some limitations. As we have seen in the match clause, we have to write this pre-ANSI 92 syntax for joins. So no joins at all, but listing the tables in the from clause. The match clause can only, what I've shown you, we can like from one point of interest connect into another point of interest, can connect into another point of interest, but this is not dynamically. So you need to know how many hops you want to go. This is not for dynamic arbitrary length queries. If you want to use this, you still have to write either loops or recursive common table expressions to find out about transitive closure, shortest path, or page rank. And there's some limitations what you can create as a node or edge table. So there's like local, global, temporary tables, or polybase is not available. And there's still no update for the from ID and the to ID, so we have manually write the update. Update is always like deleting the old row, the old version, and then you insert the new version. That's what you have exactly to do if you want to change a connection between nodes and edges. You have to delete and insert. There's no update available. And cross-database queries are not supported because everything in one database is from one graph, and there's no chance to query to another database which is in a different graph. So what's new in 2019?
Is that just for
Yeah.
graph tables? Can you join to other tables in other databases, or just the graph?
Yeah, only the graph. So if you want to use, the question was, is this applies this only for graph tables or for all the tables? Usually you can write your joins, you can write joins or queries cross databases. There's no problem at all because you just use the database name with the as a prefix to the table name. But for the match clause, you have no chance to refer to other databases.
Okay, so all the tables in your from clause have to be in the same database.
Yes, all the tables has to be in the from clause for the match has to be in the same table. Yes. So what's new in 2019? The single best improvement in 2019 is that we now have a shortest path algorithm built into the product. And now we can query arbitrary length traversals, so we can find, for example, a node which might be 1, 2, 3, 4, 5 hops away. Then we have, this is really difficult for me to pronunciate, so heterogeneous associations. If you can't understand what I'm telling, you can read on the slides. So you can combine a subquery, all your fathers, all your mothers, and then use the subquery as part of your match clause. Then the merge statement is now allowed for our graph tables, and edge constraints are added to the product. Let's see how this looks like and feels. Pardon? There's a question?
Yeah, for the shortest path, is there a limit to the number of hops it can do?
For the shortest path, there's a limit in amount of hops it can do. Not that I'm aware of. So you can either write, I forgot it. I think you can write, it should only hop like 2 times or 3 times, or you can write like endlessly. Just find your way through the graph. There might be a limitation in resources probably on your machine, but from the syntax, there's no limitation. Yeah. For your question. Yeah. So, let's play around here. So new to the product is now edge constraints. So we can create all the table and then add constraint. This is nothing new. But new is like we can have a connection keyword here. So the isFarther edge is now limited to connecting family members only. So I cannot connect all of the tables with this edge, but only family tables, for example. When we do this, this helps us in one way. Of course, like a foreign key constraint, we cannot delete then a family member which is used in one of the edges. So we avoid having orphans. And the other thing which we have is that we can then avoid that somebody connects as isFather and telling that Edward is the father of Winterfell. Maybe this makes sense for someone, but it would not be allowed in our graph because we can limit this. So if I execute this, I get this insert statement conflicted with the constraint, and then I'm not allowed to insert this. Of course, we have DMVs available. So if we are looking for all the edge constraints available in my database, we see the name here, the object ID, and so on and so forth. That's one of the new tables, and we have the constraint clauses, so we can see what is connected, and we get the object ID from object ID to object ID, so to which object the from clause is referring to. And of course, we can combine those tables, so we can write a select statement combining the edge constraint and the edge constraint clauses to make this put this more in a readable form. So we see the route, easy route, is on the route edge table, and the route table can only connect points of interests, or the isFarther edge table can only connect families. You can also mix up. So, for example, you could have a person table, and the person table is then like bought this product, and you have an edge constraint between your person and your product, and then you can limit the constraints that a person could buy a product, but a product cannot buy a person, for example. The other thing is that we now, in SQL 2019, we can now use a subquery, give it a name, and then refer this name in the match clause. This was not possible in 2017. In 2017, you get this error message telling you that the match clause is corresponding to a derived table, and derived tables are not supported. In 2019, this is now possible, so I'm looking for family members where I got an isFather, so they referred in the isFather edge, and I'm combining this with the isMother, so I get like all my fathers, all my mothers, and then looking for are they married to each other. This is what this query does, and then I can see Pension is married to Lisa, Lisa is married to Pension, and so on. Common table expressions, unfortunately, are still not allowed. So if we want to refer in a common table expression, I have like the family common table expression. The anchor query looks for everybody who is in start name. So I start at Pension. This is the anchor query in my common table expression. And then in the second query, I want to refer the family common table expression. This is unfortunately still not allowed. I get an error message telling me that, what does it tell me? Derived table cannot use derived table A in match clause. So derived tables are supported except for common table expressions. If you want to use this, the workaround is like joining the family common table expression with another node. And then you can, not a node, yeah, it's a node table, and then you refer the node table in the match clause. That's how you can come by this limitation here. And then there's the merge statement. So we can now merge some things with other things and leveraging the match clause here, which I find really, really confusing. So is anybody using the merge clause in production? Okay, a few hands, not very much adopted. And what I find confusing is like I have the match clause to find my way, my path in my graph. And then for the merge statement, I have this keyword when matched, when not matched. And those two things sound similar, but they're completely different things. While this match is referring to the path, to the pattern you're looking for in your graph, the when matched clause asks for, did I find one in the first table and the second table? So I have like, the row already exists in the destination table, then of course I update the destination table. When I found a row in the source which I could not find in the destination table, I would insert stuff. This is so a different meaning of the term match or matched. So let's go to the shortest path. I think this is the most interesting new feature here. So if you don't have GraphDB in place, or even if you have 2017 in place, and you want to find out about transitive closure, so how can I get from one point of interest to the other point of interest, how many miles is this away, you basically have to write a function for that, either a loop, or you can write a function which does the loop. So I got this function here, transitive closure. I pass in my starting point of interest, so where I want to start, and then the function returns a name named transitive closure, which has these columns, ID, node ID, level, path, and the miles. Then I begin at level 0. So before we start, we're at level 0, so we didn't hop to any node. And then I insert in this table, in the return table, transitive closure, that's the table from there above, everything from the starting point. So there's like the node ID of the starting point and just a name as the path. Then I check if the row count is greater than 0, so something happened. I could find the starting point, then I got into a loop, and then I'm increasing the level by 1 and inserting into the transitive closure table a reference to my transitive closure table. So I'm not now looking for a node which is referred by the starting point. And that's done. I'm looking over that. So for the first level, when level is 1, I get everything which is referred by the starting point, which we can see here. So I only want to filter by the previous level. And very, very important, if you're not dealing with hierarchies are not, there's no loop allowed in hierarchy. So if Edward is the father of Rob, then Rob cannot be the father of Edward. This is not possible as long as we didn't invent any time machines. But for the point of interest, for this kind of graphs, we could have loops. So it's important to check if I already have been at this node ID. If I've been at this node ID, I would not return this new row. So very long code, which you have to understand to write the thing. And if we query this, of course, this is working. I say of course, but I hope it's working. So let's see if this is working. Yes, it is working. So I get now starting point is King's Landing. You see this here in the here. So I call my function with King's Landing as a parameter, and then we can see starting from King's Landing, I can go to Ashmark, and this is 1,000 miles, and I would go over Castle Rock. Or to Esterport, this is a longer route. The shortest one would be Storm's End, and so on and so forth. So this is working. When we write this in 2019, I don't need the transitive closure function. So everything I discussed previously is not needed. We only execute this one, because in the match clause, we now have the shortest path keyword. So I'm asking, please find the shortest path from A to B going over route. And I'm not interested in any, so try to find, what do I want to see? Say, so I don't care how many hops it will take. So this is arbitrary length. And if I execute this one, we get the very same result back. And let's see how the execution plan is, because everything is about performance, actually. So in the release candidate, the shortest path was slower than my function. So I'm really excited how this looks like here. Still the same. So the function from the perspective of query costs would only be 35%. The shortest path as the new match clause would cost 69%. So something is not very performant here. I don't know why this is the case, but if you need performing queries, you should still think about writing the functions. Yeah, there's a question.
Why is Esterport further away now?
Yeah. Good question. Can I pass this over? Yeah, very good question. There's a difference in miles, not for all the rows, but for some of the miles. So if we take a look on the results, so we have like for Ashmark it's 1,000, Ashmark is 1,000, but for Esterport I got 6,055, and here I got 5,085. That's your question. And the thing is that the shortest path in the match clause, this is only by amount of hops. So this is not, it's not a weighted shortest path, it's an unweighted shortest path. So the only way it's optimizing is like the amount of hops. As I have 4 possibilities to get from King's Landing to Esterport, and the amount of hops is the same, it's just putting one of those elements. For my query here up here, I really optimized by miles. So this is a weighted thing. Yeah.
Did you add any indexes to your tables?
Yes, I did.
Nodes or the edges?
Yes, I did for the node ID and for the ID. So everything I'm using here to refer, there's an index on it. So this could be a bad message. So should you use GraphDB at all if this is not performing? And what I tried also is like comparing if I write the query in the common way of just joining tables. So I have the child table, I have a father table, and then I want to get my way from the child to the father via those IDs. This is one way of writing this without any GraphDB. Or the other way would leveraging the match clause here. And if we again turn on the query, the execution plan, and if I execute this, then we can see in this case, it's really, really close. So the traditional way is 49% of query costs according to the actual query plan, and 51 for the match clause. But as a surprise, you can then add more hops and more hops. That's what I did. So if you not only have one hop, so one join, but 2 joins, which means 2 hops over 2 edges, if you execute this one, then you can see now the traditional way is slower. The match clause is faster. So obviously, behind the scenes, Microsoft and SQL Server did some performance tuning for those match clauses. So you have to check out which one is faster before you decide on using the GraphDB or not using the GraphDB. And this is getting worse and worse the more hops you have. I think I wrote it down for up to 4 hops. This is getting better and better in favor for the match clause, and worse and worse for the traditional way of writing queries. So how I'm doing time-wise? really fast today. So any questions so far? Another chocolate for questions. Yeah, sorry, yeah.
Do you have a recommendation for indexes on the core tables? I think you did it on 10 tables, and this doc says write a non-clustered index, but one is created for you as soon as you make the edge and the node. So what do you recommend for?
Can we repeat again the question? So if you...
What do you recommend for indexing
Yeah.
on the core tables upon creation?
On the core tables?
Yeah.
Before you create the edge...
Before you make the 10 tables that you did in that demo.
Did I do temp tables in the demo?
On your function.
That's the part I didn't understand. So, you mean those queries here? This query here? This one?
I think above at the top.
At the top? So there are no temp tables.
No, back in your other example.
Okay. This one?
The function itself that you wrote.
The function, okay. There is no temp table. There's a return parameter for the function. Are you referring to that?
Yeah, I misread it.
Yeah, okay.
So do you have a strategy for certain types of indexes when you make your edge and node? Adding indexes or not, or dropping what's created?
For the GraphDB or for the relational base? For the GraphDB, before you create a table, you cannot create an index because you cannot convert the existing table to a node or an edge.
Right.
Yeah. And afterwards, of course, I would put indexes on the node ID and the from ID, so the joins are faster. I think that's what I also did. Let's take a look at the point of interest tables. Is it like here? So we can see, where do we get this here? Add constraints, foreign key constraints. Let's look for indexes. Enter a solution. This was a bad idea. Thank you very much. Management Studio. Oh, good. Okay.
Luckily, it's not being recorded.
Is it? I don't know. Yeah. So I stop with that and I go back to my slides until this is like. So, advanced stuff. This is where you can win another chocolate. So, which one of those two graphs is an undirected graph? The left one? I did look in this direction, so I assume you were the fastest one. The left one? Yeah, got the chocolate.
Thank you very much.
So I should first resolve the thing. The left one is the undirected graph because you can go both ways from Winterfell to Castle-Servin, but it doesn't make sense with any hierarchies. Hierarchies are always directed. So Rob is the father of Eddard, not Eddard is the father of Rob. The Rob, who was that? Yeah, another chocolate for you. Who was that? Was it you? Yeah. So Rob is the child of Eddard and not the other way around, of course, of course. How can we find out if a graph is directed or undirected? And that's where I switch not to Management Studio, but to Azure Data Studio. Who have you heard about Azure Data Studio? Everybody in the room? Almost everybody? Who is using Azure Data Studio? Okay. Who is not using Azure Data Studio because there's Azure in the name and he thinks this is like connected to the internet, something like that? I see people like, why should I use this? Because we're not allowed to use Azure because cloud is bad. Yeah, Azure Data Studio, as I said, I really love Microsoft for including features into existing products, but I don't like Microsoft for having clever names. So Azure Data Studio, I don't think this is a clever name for the product because it's not connected to Azure. It's an alternative to Management Studio. The advantage from Azure Data Studio is it's running on Windows, Mac OS, and Linux, and you can connect out of the box to SQL Server, Postgres, and MySQL. And it's open source, so you could even write your own connectors and stuff like that. And what I like is the possibility to have notebooks. So this is like, I could open with Azure Data Studio. Of course, I can write my scripts. I can execute my scripts, like we've seen in previously in Management Studio. So I go there and then execute my stuff there. No problem at all. But what I like with Azure Data Studio is the possibility that we can write notebooks. And notebooks are really a good thing because you can write like text, explaining things, and then you have a query here. And with the notebook, also the last execution, the result set of the last execution of a query is stored in the notebook. So everybody can see what was the result the last time we executed this. And we can always, again, execute it by running only this part, or even run all the cells so the whole thing is executed. And you can use this, for example, for installation scripts or for, like here, for training material. Explain people what you're now going to show, and then you show, actually, in one thing. So what I've got here is the first script is trying to find out if a graph is directed or not. How can we do this? What I did here is I'm joining the family tables, so going from the family over is farther to the family. We are normal joins, not the match cows. And then I'm checking with a left join. That's the reason why I did not leverage the match clause here. I need the left join. I want to find out, is there also a way back in the direction? So if I can go from A to B, is there also a way from B to A? If there is, then it would be a non-directed, an undirected graph. So if you execute this, we can see for the family path as expected is an undirected, is a directed graph, because if somebody is father of someone, then it cannot be the other way around. If you take a look on the route, so this is the very same query. I just exchanged the edge table to route and the node table to point of interest. And as we can see here, this is it's not a directed graph, because if we can go from Ashmark to Golden Tooth, we can also go the other way around. So this is an undirected graph.
So your results say whether where the node is directed.
Yeah.
I mean, where the edge is directed.
Yeah.
Not the graph, right?
Yeah. The query, yeah.
Okay.
You're right. This query is checking if the edge is directed or not directed. We could also, of course, we could also like group this and then find out if the whole thing is there only directed, only undirected, or is it like mixed. You're referring to the same?
That was my question. Is basically you can have a mix within that.
Of course you can have, yeah. I think we would have to ask a mathematician if there's at least one undirected graph, if the whole graph is then undirected. I'm not sure. I'm not a mathematician. So the next question is about cyclic. So which one of those two is the acyclic? The right. I think I heard it again here. You already had one, so I'm going over there. Really? People are really... Yeah? So the right one is the acyclic one, because in a family tree, you can imagine there's no possibility for cycles. That would be really weird. But of course, in the graph, you can have cycles. And then again, we can take a look on the query I wrote here. So this query is returning if a subgraph is cyclic or not. So if one like node there, if there's a cycle possible for this node or not. And what I'm doing here, I'm going through the whole graph, the point of interest, and looking for the shortest path between all of the nodes. So I got a combination of all of the nodes. Can go from A to B, and all possible combinations. And if I can find rows in here where A and B is the same, so I go from Winterfell to blah, 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 and returning to Winterfell. So A is Winterfell, I'm starting at Winterfell, and I'm returning to Winterfell. Then, of course, this subgraph would be cyclic. And that's what we can see here. Takes a little bit longer, so we'll not execute it here. And then we can see the subgraph for Ashmark is cyclic, and so on and so forth. Yeah, another question? Can you repeat?
Why can't you just do A with the route to A?
You're referring to this? A route from A to A. This would not be possible because, of course, if I'm referring to myself, this is not a cycle. I want to go through the whole of the graph to find out if there's a cycle. Because if I'm checking if the column A in table X is the same like the table column A in table X, of course this is always true. Yeah, got it?
I think it
Right.
stops, right? It doesn't return that output, the A to A. In a cycle, it stops on the node before the output, before the A. Before you get back to yourself, is what I think he's asking.
Are you asking this one or not? No, you could not hear. Can you repeat again? You think that the cycle is stopping like one node before?
Yeah, well, in the A to A, it would have to have a connection to itself directly, right?
Yeah. I mean, we can try it. I don't think this is even possible to write query like that, but I never tried. So let's take the chance, and then we execute this. Is this working? No. The table name or alias A must be marked as for path. Okay, then we have to write Then I would have to rewrite this thing because I cannot refer the same table there. If I write for path here, I'm not sure what it's going to do because I'm then starting. Yeah, this is just not possible to start. Is it for path? Here we go. Never type in a demo. Was not used. Yeah, we can rewrite this. Let's try this out. No, also, maybe it's just my query that it's not possible to rewrite this. But again, even if it's graph, think of a normal table, and if you're checking if the content of like A is the same like the content of A, this is always true. Yeah. So we have to like write a query where the thing is going from one point of interest to another point of interest. In fact, it can be the same node, like Winterfell, but we have to refer it in two different things. There was only a question here. Yeah.
So in Neo4j and Cipher, you have this idea of collect, which is like their version of a group by, to collect along the way the properties of the edges or the distances.
Yeah.
Is that supported, or can I do group bys?
So the question is, in Neo4j, in the original version of Cipher query language by Neo4j, there's a lot of different operators, like collecting to group by stuff. This is just not possible in the implementation of SQL Server. So the team is like underfunded. I think they know how cool those features would have been, but currently we don't have these features. There's a lot of more features in Neo4j. So it's just a small amount of the implementation of Neo4j's Cipher query language is available in SQL Server, unfortunately. Yeah?
So to do the distance-weighted graph, you would have to do it as a function?
Yeah, that's, yeah. If you want the weighted shortest path, you have to write this on your own, like I did with this function, the transitive closure. So there's no way to leverage any of the functionalities from the match clause.
Couldn't you put that in your where clause? If you have numbers for the edges, couldn't you start to filter out which edges to include in your where clause?
In the where clause, what do you want me to write in the where clause?
It's a map, so it's got so many properties. Doing all paths, so how can you find this?
I think you're referring to what I did. Now I have this 1,000 tables open. Yeah, there's a lot of examples, so we could talk much longer. What I'm looking for the first stuff there. No, it's sorted alphabetically. So I think I was there, the shortest path. Oh, no, I can't find it anymore.
It's not important. Keep going.
Like here. So what I did here, like I added up the miles. So this thing. So this is not the mile between King's Landing and Storm's Land, but it's the miles added up for the whole of the path. This is what you're referring to. Yeah. And unfortunately, we can use this like here in the select clause, but we cannot refer to this in the where clause. This is just not allowed. So there's still some limitations there.
So to restate that, are
Yeah.
you not allowed to explicitly say
So your question is, can I exclude a certain point of interest? Like if you go your way and you want to avoid some edge because there's like traffic jam. I don't think this is possible because in the merge class I have no chance to tell my shortest path keyword to avoid some of the nodes. I can filter, but I could in the work class I could filter and then avoid this kind of node.
In the where clause or the derived table, right? You can do that in the derived table.
Or do a CTE and eliminate where that edge is present.
Yes, because if the edge is not like available in the query, then of course it will not be used. So this is possible. Yeah. Another question? Yeah. What tools do you use to visualize the graph data? So still in Management Studio and Azure Data Studio is not a visualization tool. We only get lists. If you refer to Neo4j in their query tools, of course, they visualize all the graphs in cool ways. The only tool I used so far was Power BI. In Power BI, there are some custom visuals available where you can then export or import or whatever you look at it, the result set of your match class or whatever, and then visualize in Power BI. That would be the way I would go for it. Yeah, another question? Can you convert the table? Okay, you already have in the table and you want to convert it to edge and nodes. This is not possible because the only way you create a table is a node or an edge is by having the S node or S edge constraint there. So to convert it, you have to create it and then using insert statements to move over all the data. So maybe a migration project could be slow because you have like to copy the data. Yes. The questions, yeah?
Any support for more generic algorithm that shortest path, that's pre-GALE or level propagation, commonly used in larger datasets for graph algorithms?
So is there an algorithm in Match for what?
Level propagation, pre-GALE algorithms?
No. The only way now is like the shortest path, unweighted. There's no other options like stating special algorithms you want to use.
Whatever you do, usually in graph database.
Yeah. Still not available. I think the team is aware of the lack of the features, but there's no good answer I can give you. Yes, there's an algorithm because there is no algorithm. So heading back to, I think we stop here. So which of those two graphs is an unconnected graph? Yeah, right, you already got one chocolate. Who didn't have a chocolate? You didn't have a chocolate, I guess. The left one is the unconnected graph. So if I find one node which is not connected with the rest of the graph, then the graph is an unconnected graph. Usually hierarchies, so one hierarchy itself cannot be unconnected. If it would, then it would be like two different hierarchies. And we can again check if we can find connected versus unconnected graphs. So what we can see here is I'm checking how many number of paths I can find. So I get a list of all the possible shortest paths I get. So I get one connection from one node to all the other connections, one row per possible connection. And I'm counting how many nodes I got there, and then I can find out like if the number of paths from one node is exactly the number of nodes in my graph, then it would be a connected graph. So if we take a look here, for example, from Ashmark, I can connect to 78 other nodes, but in total we have 148 nodes in my demo database, so this is probably not a connected graph. And there's even, for example, Bloodygate. Obviously, I missed Bloodygate out, so this is only connected to one other path, as we can see here. So we have if I limit the search to Bloodygate, then we can see Bloodygate is only connected to the array, and theoretically, Bloodygate would be connected to itself. So this is the unconnected part of our graph here. And then the unweighted graph. So which one is the unweighted graph? Right. Somebody was really fast here. You were? You already got the system, yeah? So the right one, hierarchies. Usually hierarchies are unweighted because it's really hard to tell your children that you love the other child more. Even my daughter accused me sometimes that I love my son more than her, but this is ridiculous, I guess. But for point of interest, for example, we could have weights assumed, and we can find about the weights. What I did here, I just queried the metadata of my tables. So if I can find an edge table, so the table is an edge, and it's not a graph column, but it's the other column. And if there's a prediction non-equal 0, and it's not bit, then I assume it's a numeric column, and then I assume it's a weighted graph. Doesn't have to be really the right thing, but that's how we can find out, are there any numeric attributes for the edges. And we can see for the route edges, we have the miles per land, miles per water miles. We didn't see previously the recipe. There's also amount attached to the recipe, so how much of flour I have to put into the recipe, for example. And the last thing here is the degree of a node. Can anybody tell me what the degree of Winterfell is? 2. Who was this? Yeah, that's a difficult question, so you earn a second chocolate. Can anybody tell me what the degree of Maud Kaelin is?
2.
It's also 2, yes, very good. So the answer is not always 2, but it's the correct answer is the amount of edges which are going or coming into a node. So Winterfell would have a degree of 2, Castle Severn and White Harbor a degree of 3. And the degree of node is interesting because this can be used to find out which of the nodes are more important. So if you think you tear down Castle Severn, so you cannot go anymore over Castle Severn, then this has a bigger impact than if, for example, if a remote city is not available more. There's different ways and different kinds of centrality. So what I did here, I came up with a query counting the amount of connections. So I'm having here my point of interest, and then I'm joining the outgoing ones. So from my point of interest, how many refers do we have, or how often does this node is referred in the from ID? So this is like the outgoing connections. How often this node is referred in the to ID of the route. And then I'm checking if there's a value returned, and then I'm summing this up. So I'm counting how many connections do I have outgoing, counting how many edges I have incoming, and then I can add this up, and I can even show an average, so I see what is the average in this graph. And if we order this by this degree, to no surprise, you see, for example, King's Landing popping up at the very top, because King's Landing is connected. There's many connections going in and coming to and going from King's Landing. So the average would be 16, and this is a degree of 98 if I sum up both the outgoing and the incoming edges. Or if we go down to Liz, this is far away. There's not so many connections. This is more an average country from the terms of degree centrality. We can also calculate a different centrality, which is the closeness. So how close is one node to all of the other nodes? Like finding out what is the middle of the US, for example. That would be the idea behind that. And there we have to sum up the miles by all the paths available from one point of interest. To make this faster, I build up a data warehouse table, so we have like faster queries here. So if you execute this, it should be really fast, because all the paths and all the information is persisted in this table already. And we can see Bloody Gate, for example, is very central, because Bloody Gate is only connected to array. So for this subpath, those two are really equal. If we go to the path to the other graph, where all the others are connected, so Mir, for example, would be very central, in the terms of that from Muir to all the others, if I want to go from Muir to all the others nodes, it's only, what is this, 188,290 miles. Ironwood is also very in the center of this Game of Thrones universe. Another centrality would be the betweenness. So the betweenness is like how often are going other routes over this route. So this would be an important thing if you think about IT architecture and you're looking for the single point of failure. So all the other connections are going through a firewall, for example. Then the firewall would be very central. If the firewall fails, you have a problem in your whole system. This is how you can find out about that. So I'm splitting up the path. So I get like a vertical list of my connections. And then I'm counting how often a certain point is mentioned in the path. So we get this list, the King's Landing, for example. Many of the connections I entered into this demo database are going through King's Landing. So King's Landing is very important, so to say. And the different one would be, let me have this. Different term here is if a node is pivotal, then it's referred by all the other nodes. I don't have any pivotal node because I think there are in my demo database are not all connected. But if I limit this to only the way between or the path between Moat Kelly and Storm's End, we can see if I want to go from Moat Kelly to Storm's End, I have to pass Castle Serwyn, Winterfell, King's Landing, or White Harbor, Winterfell, and King's Landing. So Winterfell and King's Landing is very crucial that those are available for my path if I want to go from Moat Kelly to Storm's End. And the first one is the shortest one. So maybe my GPS system would list me the first one to go because this is the fastest one. If I have troubles here we go. If there's a problem, for example, with Castle Serwyn, which lies on the shortest path between those two, I can also find, and this is like the answer to your question. Who was it? Your question? Can I avoid a certain point? Yes, we can. We can already see this here. I forgot about that I have this in my demo. So I can avoid all the paths going through Castle Serwyn, for example. And then I end up with the only way from Moat Kelly to White Harbor to Storm's End by using the other route available. And what else? The betweenness centrality identifies the control points. So what we get here is like how many shortest paths do I have from a certain point. No, this is just a different implementation from the same thing, which was not really faster. And the very last thing before we got to the end is the PageRank algorithm. It's also very important if you talk about graphs. So PageRank invented by, what's the first name? I always forget. Sajid Breen and the Google guys.
Larry.
Brian, yeah? Brian Page. And the thing is it named after Brian Page, or is it because it's like pages, web pages they're looking for? And the PageRank algorithms tries to find also the importance of a node or of a web page, to be more concrete. And the algorithms tries to apply to find out a node is important if it's referred by many other nodes. Of course, if I have a web page and all the other web pages are referring to this web page is obviously more important than some page which is not referred that much. But additionally, it's weighted. So if an already important page is pointing to my page, then my page is more important because an important page is pointing to my page. And of course, you cannot calculate this in one round. You have to iterate. And that's what this implementation is doing. So we're starting a loop here and then going through the graph several times to recalculate the importance of a node by calculating how important the other nodes are referring to my node. And if we execute this, we can find out, for example, then Storm's End and King's Landing and Winterfell are the most important nodes in my, or most important points of interest in my universe because they are like very central. Many of the routes going through or to Storms End, King's Landing, and Winterfell, and important point of interest are also going to those countries, point of interest. So with that said, I can wrap my talk up. So what I did show you was the GraphDB 101. What is a graph? Nodes and edges, which are connected. Then we took a short look at what happened in 2017, where GraphDB was implemented. And we have nice additions in 2019. And then we took a look at examples where we can query and find out about the graph. So I hope you learned something. I hope you learned more than Jon Snow. Jon Snow knows nothing, if you ask Irgrid. So this is my favorite pie chart, a 100% pie chart. I think that's the only way you should use pie charts. With that said, are there any questions? Are there more questions? Yeah?
In your opinion, is it worth using GraphDB and SQL Server yet?
Is it worth to use SQL Server GraphDB yet? Depends on the use case. I'm a consultant, so I will always say it depends. I think there are use cases, but they are narrow. For example, if you think about like, if you have to query graphs conventionally with joins and then use the match clause at a certain amount of joins, it would be better to have the match clause performance-wise. So this would make sense. And the second thing, maybe the shortest path implementation is not as efficient as writing the function. But maybe it's easier for you to maintain, instead of maintaining functions using this, let SQL Server find out the shortest path. If you don't need weighted graphs, weighted paths, it would be a feature you should use. So check it out. There's no clear answer. It really depends on your use case, I would say. Yeah? Another question back there?
The thing I need often in graphs is like a topological sort for topological ordering. Is there a recipe out there for that? Or would I write that?
Can you speak up louder?
Topological ordering.
Topological ordering? What do you mean with that?
Family, there's like a family tree, right?
Yeah.
So I haven't seen Game of Thrones, but there's like a lot of incest in it, right? So if you wanted to list of ancestors and descendants, just to know the order, like there are multiple paths. So it's a way to get one of the paths quickly. I'll come up talking to you about it.
Yeah, okay, yeah. So I'm afraid that there's no solution for that because like the match clause itself does not allow for any algorithms, and then you would have to implement it in your own loop or commutative expressions.
Can you go
Yeah.
back to resources? Just show.
This one.
Is your notebook available?
Yes. So I put it already, gave it to the guys from Path Summit, so you should be able to download it, I think as soon as the recording is available. I'm not sure how the download works. If not, just shoot me an email and I will be glad to send the things to you. If you want to come to Vienna in January, which is very nice, we do a SQL Saturday in January, which is on a Friday actually. We can talk about that afterwards, why it's a Friday and it's called SQL Saturday. Other than that, if you like the session, please fill out the session evaluations. Otherwise, have a nice day.